demonstration we call the tennis ball resonator experiment. So you can see what we've got. We have tennis balls suspended on the end of these brass rods, or we also, in this case, have a wooden dowel rod. And it's pretty fun. So one of the things that you could do, we typically either have this set up where it's bolted at one end and you can shake it like this, or sometimes, let me just take this off of here. You could set this up like this, where now it's free to shake back and forth, or you could shake it this way. Or we also could take out this rod right here, and you could put the hole over here. So you could set this up in a wide variety of ranges. So you can either put either hole on the bolt, or you can have some other wooden dowel rods in here and just shake it freely. So let's take a look. One of the things that you might ask is, do you need to shake this apparatus at high speed, or I should be careful, at high frequencies or low frequencies to make the large rods shake? So you come up and then you try it, right? And if you shake this thing quickly, you can see you can get the small one to go at high frequencies, but if we go at very slow frequencies, we notice that the long one goes back and forth a lot compared to all the other ones. And then if you speed up a little bit, notice we're getting these other two guys going. It gets pretty crazy. And different frequencies, let's calm this down and take a look. Different objects have different resonant frequencies. All right? And so if we go a little bit faster here, notice that we can get this wooden dowel going pretty good at high frequency. And you might start wondering, well, wait a minute, I thought large objects tended to have low frequencies, and that's a good point to bring up. At this point, you want to remember there's several factors that will influence the resonant frequency. One is the length of the object. Typically, longer objects have lower resonant frequencies, so you need to shake them with a lower frequency rather than the higher frequency. All right? The mass distribution matters. By putting a ball on the end, that's going to lower these frequencies. So that's changing the mass distribution. That also has an effect. If you wanted to learn more about mass distribution, you could read about the figure skater demonstration or the moment of inertia wands, and, or you can take a physics class. Also, the stiffness of the material tends to make a difference. You'll notice that this wooden dowel rod is a larger diameter than this brass rod. And so as a result, it's a little bit stiffer. So even though it's longer and you would expect a lower resonant frequency, the stiffness tends to increase the resonant frequency. So there's a lot of factors here. You've got mass distribution, right? Is the mass all at the end, or is it evenly distributed? Okay. You've got the length. Is it very long or is it very short? And then you've also got the stiffness here. In this case, this is very stiff as opposed to this. So more stiff, higher resonant frequency. Longer, lower resonant frequency. More mass far from the pivot, or large moment of inertia, lower resonant frequency. And so you could try this again. Let's take one more look here. And notice, let's try I like that lowest resonant frequency. Notice I'm not pushing this thing very far each time, and yet you get this enormous motion. So you don't have to push very far. The distance that you're shaking this back and forth is called the amplitude. So you could get this going with a very small amplitude. There's a great analogy with a person on a swing set. When you push someone on a swing, you give them a little push many times over and over again, and they gradually get up to larger and larger heights. And so you could see that by pushing a small amount at a certain frequency, they're going to gradually increase their amplitude. It's basically the same thing. By pushing a small amount over and over again, you can get this thing going to a large amplitude, much larger than the amount I'm pushing it down here. Same type of phenomenon. Again, this is called resonance. Now, if you shake it really fast, you might even be able to get harmonics, and if you wanted to learn about harmonics, you could look at the resonant rings on a speaker demo. Some other demos that go well with this. Obviously, buildings shake like this in an earthquake, so you might look at our shake table video as soon as we get that done. We also will have a Chladni plates video you could look at, and the resonant rings on a speaker, or standing waves on a string. If you wanted to read in a physics book, that's a good place to start as well. Or resonant frequencies of sound in a pipe. So there's a lot of different ways resonant frequencies pop up in real life, and that's kind of fun. And this gives kids a hands-on way to play with that.